Do you hear me from home?
Sì, la sentiamo.
Okay. Okay, so what I want to do today is to start discussing with you an example of a technique that we started introducing yesterday. So let's first of all it was here, no? Yeah. Let's first of all recall a moment what we did till yesterday. Sorry. Okay. So this technique that we are studying is what is called finite elements, and as I told already quite a few times, is based essentially on three ideas. First idea is that you rewrite your problem from your boundary value problem. Instead of having a differential equation with boundary conditions, you rewrite as a sort of integral with the idea that you are finding a function, sort of test function u, that is written, okay, is this object, this one, essentially. You are finding a function u such that for whatever v, this relation is satisfied. K is the function that enters the differential operator, and f is the right-hand side of the equation. Can be the external force or external source or whatever, depending on the details. So this is the first point. The second point is the Galerkin technique. So this Galerkin technique tells us that instead of having to deal with a space like, let's say, L square, which is infinite dimensional, you restrict yourself to a finite dimensional space, and that there is a way to check that what we are doing is consistent, meaning that we take a subspace of, let's say, L square. Typically, the subspace is finite dimensional. And what we claim is that it does make sense to solve the equation restricted now to the subspace. So essentially what we are doing is that we are looking for a Vn. There is this notation a little bit strange because U is the solution of the original equation. Now we call Vn the solution in the subspace, the approximation to the solution in the subspace. And the test function, the V, is also restricted to the subspace. Still, this equation, that is the one that really we are going to solve, does make sense because it is easy to show, as we have done here, that Vn obtained by solving this equation is indeed the best approximation to the exact solution within the subspace Vn. Okay, so this is the second step. So we have at least an equation which is written in a consistent way and that works in a finite dimensional subspace. And so in principle, we can solve that equation. Still, it's not very efficient. The reason is that, okay, we can choose our base for the subspace, but we still have a problem. The problem is that after we expand everything on this base, we expand, for instance, f on this base, and the equation becomes an algebraic equation, because we also expand, of course, the solution of the same subspace. So we end up with this algebraic equation, and okay, if the dimension of the base is small, there is no problem in solving directly this equation, just using whatever linear algebra algorithm that allows to compute U in terms of the matrix K and of F, essentially by computing, for instance, the inverse of K or whatever. This, of course, in principle it's easy. The problem is if you deal with complicated real-life problems in which the basis on which you are expanding is very large, and I provided a little example showing that there can be situations in which the base can contain millions or tens of millions or more of elements, and therefore at that point your matrix is a matrix of 1 million times 1 million or more. Okay? Then it can be very time consuming to solve directly this equation by computing K2 minus 1. And therefore we discuss another idea, which is the one that really enters the so-called finite elements technique. The other idea is maybe we can choose a basis that is such that the matrix K will be almost diagonal. As we will see today, is 3 diagonal in using a specific. Oh gosh, scusate. Si fa spegnere il cellulare, non basta pigiarlo. Benissimo. Scusa. Vabbè. Ok, sorry. What I was saying. I was telling that, okay, we try to find a base that is essentially providing a matrix K which is almost diagonal, 3 diagonal. Okay, so this was, to say, an example not taking into account that idea. I mean, just using instead a normal base, for instance, sinus functions. And of course, it works, it's not a problem. Sinus functions are easy. We can therefore compute a lot of integrals even analytically. But it will not, I mean, the problem is essentially that we end up in the general case, in this specific case here, the K, the matrix was diagonal. After the next example that we studied, the matrix was already not diagonal. So it is clear that in principle, one has to invert this matrix not diagonal. And as I said, if the matrix is not too large, no problem. If it is very large, we run into troubles. So, okay, what we want to do today is to discuss a little bit more in details what is this basis of linear piecewise functions. So piecewise polynomials, but we will concentrate just on linear functions. So the idea, as I said, is to build a basis made of objects like this one, sort of triangles. But let's try to be a little bit more formal today. So how do we build such a base, and are we sure that is really a sort of base, etc., etc. So first of all, let's introduce. I mean, you recall we start from, let's say, L square, and from L square we go to a subspace that here is called Sn. And this Sn is a subspace containing functions which are linear between points on a grid. So let me define slightly better this point. So we have our interval, let's say from 0 to L, and we divide our interval into points of a grid. And the idea is this subspace Sn, therefore, contains functions which are linear between each point on the grid. So, for instance, a function like this, okay. This is an example of a function that notice that I have chosen a function that is vanishing at the two extremes, so that this would be L square restricted. So is the subspace of L square of the functions which are vanishing at 0 and at L. And so this is the subspace we are now considering. We are considering a subspace of functions which are continuous, and we can integrate also these functions, but they are made of straight lines, like indicated here.
Prof?
Sì.
Scusi se la disturbo, posso chiedere
certo.
per favore di mettere la penna un po' più nera perché faccio fatica
Sì, certo.
a vedere.
Sì,
Grazie, mi
certo.
scusi.
No, grazie, l'ho detto. Proviamo a vedere se questo funziona meglio. Va meglio adesso? Is better now? This one?
Sì, scusi, non riuscivo a rispondere. Sì, grazie.
Ok, allora. Okay, so what I am claiming is that if I restrict myself to this subspace Sn, and if I have introduced that basis of functions that I discussed here, I mean these functions are functions which are essentially triangles. Let's call this basis phi I of x. So this phi I of x, this is one of these objects, and it is 0 everywhere else. Okay. I am going to write explicitly, and we will have in the numerical code, of course, we have to write explicitly these functions. So we have how many of these functions? Notice a little technical detail. Let me do it here just to clarify this point. How many functions do we need? So let's take, for instance, I don't know, five subintervals. Okay. So this, if you like, you can call x0. This is x1, x2, x3, x4, and this coincides with x5. I have taken, let's say, n equal to 5, meaning that I have n equal 5 subintervals. So how many functions I need? I need the function this one. So I need 4 functions. I need functions phi I of x, where this I is running from 1 to n minus 1. Okay. Why I don't need phi 0 or phi 5? Because we are, for the moment, considering only the problems in which the solution is vanishing at 0 and at L. So if we extend this discussion to problems in which the Dirichlet boundary conditions are not homogeneous, where I put that the solution at the origin is equal to a number different from 0 and the same here, then I will need the other two functions. We will discuss this probably in another lesson, the next lesson. But for the moment, we don't need. So for the moment, if we have divided the interval 0L in five subranges, we need only 4 of these functions. And what I'm claiming is that I can write whatever function p of x belonging to Sn. Sn contains all the functions which are continuous and linear between points on the grid. So whatever function p of x belonging to this Sn can be written as a sum. And okay, also recall that I have imposed the condition that the functions are vanishing here and here. Can be written as a sum on I running from 1 and n minus 1 of certain coefficients, and the coefficients I'm claiming that I can fix in this way, p x I times phi I of x. This is what I'm claiming. So this phi I of x, I have not written the analytic expression. We are going to write it in the numerical code. But okay, it is one of this object. It is 0. So in particular, let the properties which are particularly important, phi of x, is that phi I of xi is equal to 1. Or if you prefer, phi I of xj, j is equal to delta ij. Okay, meaning that the only point on the grid where the phi I is different from 0 is the point where x is equal to xi. As we see, this was phi 1, phi 2, phi 3, and phi 4. Okay, and the other properties as defined, as you can see, that outside of the interval. So if I take phi I of x, this is an I, for x is equal to 0 for x larger than xi plus 1, or for x smaller than I minus 1. Okay, these are the properties that we can use in our discussion. Okay. So how do I show that this is true? How do I show that whatever linear function, linear I mean between the points of the grid, okay, belonging to the subspace Sn, can be written in this way? Well, it is very easy, because recall that these functions p of x are completely defined by the values that the function takes in each of the points of the grid, because in between the points of the grid, by definition, they are linear. So the only thing that I need to check is it true that this expression here provides for each of the points of the grid the right value? Well, yeah, because if I take p of xj, where xj is one of the points of the grid, so we just substitute and what I get is phi I of xj, but phi I of xj is delta ij, and therefore this is just equal to P of xj. Okay. So this basis, this set of functions is sufficient, so to say, to expand whatever piecewise linear function. And actually, it is also linear independent in the sense that it is not redundant. It's trivial to check. It's essentially exactly the same calculation. Suppose, for instance, you recall that to check if really the elements of a base are linear independent, you ask yourself, what happens if I make a linear combination, no, of the elements of the base? I take a generic linear combination, so let's say Ci of phi I of x, and I put this equal to 0. And to conclude that the elements of the base are linearly independent, I have to check that this is true only if Ci, they are all equal to 0. And okay, this can be done again exactly in the same way. Let's take x equal to xj, for instance. And so from here, I get that the sum from 1 to n minus 1 Ci phi I of xj is equal to 0. But this object again is delta ij. So this is just the sum. So, sorry, no sum. Oops. Let's go now. Oops. This is just delta ij kills the sum, so this is just Cj, and this must be equal to 0. But this, of course, is true for whatever j. So it means that if I put to 0 the linear combination of the elements of the base, then the coefficients, they must be all equal to 0. So this is a base, is made of elements which are linearly independent, and they can span completely as n. Okay, so the next step is to try to, okay, let me comment again before looking at an example. Let me comment again on why this can be useful. So you recall that we have essentially to compute a matrix, the matrix Kij, which is defined as A of, let's say, phi j, phi I, meaning that is an integral between 0 and L, dx k of x, and here you have derivative of phi I over x, derivative of phi j over x. So why this matrix is, as I mentioned already a few times, tridiagonal? Well, the point is the phi over the x, the phi I over the x, the phi j over the x, I mean, they are different from 0 only on a very limited range of values of x. So what happens? Suppose that I take, let's say, j equal to I, let's say, plus 2. So the question is, okay, first of all, we have defined the functions more or less here. We can define also the derivative of this function. Let me do, maybe it's more clear after. So the derivative of those functions, so instead of phi, we plot the phi over the x. Okay, so this is again L. And sorry, as you can imagine, what happens is that the first function, the phi 1, the derivative is constant from here to here, and is again constant and equal and opposite to the previous value from here to here, and similar for all of these objects. So essentially, each of these objects, let's say phi 1, the derivative is something like this and like this. And this is phi prime 1. And after you repeat, okay, I mean, you understand, you have something like this, and like this, like this, and like this. So what happens when as I said, I try to compute this matrix with, let's say, j equal I plus 2? Well, of course, what enters is the phi I over the x, the phi j over the x. But as we can understand looking at the little drawing, so this one is x1, this is phi 1, so this is overlapped with the derivatives of phi 2, because of course the derivatives of phi 2 are something like this and this, and therefore this is phi 2 prime, again phi 2 prime. So there is an overlap in this region here. So phi 1 prime and phi 2 prime, they overlap, but if I take phi 3 prime, of course phi 1 prime and phi 3 prime are never overlapping, meaning that this object here is just equal to 0. Does it make sense what I said? So essentially the point, I don't know, it's strange, I cannot shrink the screen. It should be doable, but apparently I must have done something wrong. I cannot really shrink back the screen anyway. Okay, so the crucial point essentially is that since this function phi I and similarly their derivatives are different from 0 on a very limited support, then if I take, for instance, j equal I plus 2, then these two objects, one of them at least, is equal to 0, because they are never overlapping. And so chi ij is different, is equal to 0 for j equal, for instance, I plus 2. So the only values of chi ij which are not vanishing are the diagonal ones, chi ii, and chi I plus or minus 1. These are the only elements which are different from 0. So this means that we have what is called a three-diagonal matrix, a matrix which is different from 0 on the diagonal and on the two other diagonals, the one just above and just below the main diagonal. And there are techniques that I will mention, which are much more efficient to solve this linear algebra problems if a matrix is three-diagonal than for a general matrix. That is intuitively obvious in the sense that we don't need, so to say, to compute all the numbers which are in a n times n matrix. We just have a strip of numbers different from 0. And so if we are smart enough, we can dramatically reduce the complexity of the problem. Okay, so at this point, I think that it's better if we discuss an explicit example. So I will discuss the example first with paper and pencil, okay, laptop and my special pencil. And after we have a look of how I try to implement this using Python. And by the way, since I said I always forget, I will pass you everything that I have up to now on that Google class, so that you can also play with it. Okay. So let's first introduce this little example. The example is the example 5.18 of the book. Okay, so I have finished this morning to translate to Python the program solving this that I had with Mathematica. And so the little example works like this. We want to solve the equation minus second derivative of u respect to x squared equal to e of x, 0 x 1, and as usual u of 0 equal to u of 1 equal to 0. Okay. So this equation can of course be solved analytically. You just needed to integrate twice the equation, and the exact solution, let's call the exact solution u of x is subject here is minus exponential of x plus e minus 1 x plus 1. Okay, so this is the exact solution. So now we try to see how to solve this problem using the technique that we have outlined. So the first point is to build our grid. So the grid is the one that I discussed now a few times, no? This one. And we can write the analytic expression of these functions. And the analytic expression is the following. After we have this in the numerical code, of course. Phi I of x is equal to 1 over h x minus I minus 1 h, and this is for x between xi minus 1 and xi. Oh, what is h? H, of course, is this. Okay, this is h. So h is equal, in our case, to L divided by N. Okay. H is the step on the grid. Okay. So this is on the left-hand side, so to say, of the function. The right-hand side of the function is minus 1 over h x minus I plus 1 h. So this is for xi smaller than x smaller than xi plus 1, and of course is 0 otherwise. Okay. So these are the functions, and of course we can easily compute the derivative of the functions. This is one point that we can do if the functions are, of course, just trivial linear functions or whatever. It can be slightly more tricky in a more general case, but anyway. So the derivative, the phi over the x, is even simpler because, of course, it is 1 over h in the first interval, this one. It is minus 1 over h, the second interval, 0 otherwise. So in this specific case, let's go back to the equation. In this equation here, of course, the k is equal to 1. this equation here. So this means that our matrix is extremely simple, because the matrix Kij, of course, is just k is equal to 1, is just the integral of this type of objects. So we have already noticed that it is tridiagonal. So we can compute essentially two cases. The case in which I is equal to j, the case in which I, or vice versa, is equal to j plus or minus 1, and the other cases in which we know already that is 0. Okay. So let's start from the diagonal cases. So if we take chi I, it means that we have to compute that integral between 0 and L, in principle, of what? Of k of x, that is 1, and after we have a derivative d phi of x squared, because it's d phi on respect to the x and the gain. So this is just the integral between 0 and L, the x of d phi over the x squared. The phi over the x squared is 1 over h squared in all the interval where it is not 0. And this is not 0 on an interval which has a length 2h. It is 2 of these steps. I mean, if I take one of these objects, they are different from 0 on a range which expands on h and h to h. So this is just equal to 2h times 1 over h squared, which is, of course, 2 over h. Okay. And similarly, we can compute, let's say, ki I plus or minus 1. Because this, of course, is the same integral. And here we have phi I prime, phi I plus or minus 1 prime. And so these two functions, the derivatives, they overlap just on one interval having a length h, and they have, of course, the derivatives have opposite sign, because one of them is taken rising and the other is taken decreasing. So the length is h, and the function is minus 1 over h squared. Therefore, we get minus 1 over h. Okay. So this is our matrix that in this case is very trivial to compute. In the general case, we will have to resort to some numerical evaluation of the integrals which define this matrix, of course, okay, in the general case. But in this case, we really don't need to do that. Oh, which is the other ingredient? The other ingredient is the expansion of the function f. This is our function f of x. And we have to expand this function f of x on the same base. So we have to do something as f phi I, which is defined as the integral between 0 and L, the x of f of x phi I of x. Phi I of x are these functions that I wrote a moment ago, And in principle, this can, a of x, recall this object here, in this case, is just exponential of x. So it is clear that in this specific case, this function can even be evaluated analytically. Since this is just true in this specific case, I will not spend time in, I mean, if you do this, the exact result, you can get it, is exponential of I. Notice that this I is the number I, is not the imaginary I, okay? Exponential I h over 2, sorry, over h, and you get exponential h plus exponential minus h minus 2. It doesn't matter so much. We are going to evaluate this numerically, because in the general case, if f of x is a more complicated function, you will not be able to perform analytically the integral, etc., etc. Okay, so at this point, we have set our problem, because we have our matrix K, we have our column F, and we are looking for some Vn such that Kvn is equal to F. Okay. So this is what we will do, and this Vn, inside this Vn, there are, I mean, Vn is composed of numbers, which we call U actually. No? There is U1, U2, Un. These numbers are the expansion of the solution approximated inside the subspace on the elements of the basis. So after, at the very end, the solution is what here we call the U. The U will be U of x, will be written, of course, as sum on I running from 1. Actually, this is not n, to be precise, this is n minus 1, because you recall that we don't need the un, okay? So it's from 1 to n minus 1 of this un, and our basis phi, sorry, ui, okay, this is ui, phi I of x. So let me just remind again this point. If we have divided our interval in n subspaces, so for simplicity I call this subspace Sn, but recall that the number of elements of the basis contains n minus 1 functions, because we don't need the phi 0, we don't need the phi n. So also the number of coefficients is, of course, n minus 1, which is written here. Okay, so what we are doing now is to try to understand how to do this using Python. Okay, and maybe before doing that, I can do what I promised many times, which is to share with you on Google Class the programs that I have. Now, instead, you have to help me in recalling how I go to Google Class, because, of course, I already forgot. So how does it work? I do Google Classroom, and it's here. And after, maybe it's already here. No, because I entered, no, sorry, this was the other, my account. How to go back? No way. Forse qua sotto, forse. Un altro account. I have to use this one, yeah. This one. Okay, but if I click here, probably, isn't it? Don't want this nice information. Okay, so now share something with your class, I think, and add and file, browse, I guess. Let's see, browse. And it is inside lezioni, metodi matematici. Okay. And so, oops. Okay, so the only one that I put, I think, is the predator prey, I think, isn't it? So let's share the other ones. Probably I have to do one by one, isn't it? I cannot. Okay. Okay. Add. No, I cannot. Posso. Sì.
Se tiene premuto CTRL e li seleziona tutti.
Ok, allora proviamoci subito.
Cliccando uno alla volta.
Così fino a qua sotto proviamo a fare.
Allora,
ok. Vediamo se lo fa. Vediamo se trasferisce questi aggeggi. Ok, sembrerebbe. Can you also see all these files here?
Yes.
No. Okay, fine. Then. Okay, so we discussed. Sorry, I never really cleaned up the 5556. You recall that there was a comment that most likely was wrong. So please clean up yourself a comment. I recall that there was some comment that was not totally correct, but I forgot to clean up. This example I never really discussed with you, but maybe it's not so important. The one that is important today is the 518. The 518. Non è già fatto. How to have to do? Share with your classes here? No. Is not share?
No, perché prima deve scrivere un commento lì, dove c'è scritto share with your class, deve scrivere un commento.
Qualcosa.
E poi giù, esatto, e poi giù c'è il pulsante post che permette di
impostarlo. Ok, grazie. Post. Ok. You got it now? Oh, ok, grazie, scusate. Vabbè. Before, the example is this one. I have already all these things open because I was working on that this morning. But so this is the example that I want to discuss. But before that, let me discuss some little preliminary things. Sorry, just. Preliminary things. So, as you maybe already know, there is an enormous amount of material that you can find online. If you Google something, I don't know, 3-diagonal matrix, Python, you get plenty of whatever, examples. And so we have to select a little bit the material, as this is what I try to do. So for instance, because we are going to use 3-diagonal matrices and all that, so before really writing this object here, maybe let's discuss rapidly 3-diagonal matrices using Python. So what this code is doing is very trivial. If I recall correctly, it's just 3 different examples of how to write 3-diagonal matrices. So the first I got from internet. Let's have a look here. So as usual, I imported NumPy, and there is this little command essentially that allows you to build elements of a matrix. So let's recall what we want to see. Look at the examples here. Look, for instance, at the, I don't know, the last example, this one here, this one, okay. So we want to build something like this. So this object, for instance, on the main diagonal is 3, 3, 3, 3, and there's -1, -1, -1 on the upper diagonal, same on the lower diagonal. So this is what we want to do. So the general idea is that you can avoid filling one by one all these elements that can be quite lengthy, just by, the complete matrix, just by telling the elements which are non-zero in the diagonals. So for instance, this command here, let me remind you, np dot means is a comma diag exists inside the package np, which is NumPy. Okay. And this diag essentially is telling you fill a diagonal with all a, all numbers all equal to a, okay? And this diagonal, respect to the main diagonal, has an offset k1. If you look at the example, it should be more clear. Oops. So this is what you get. This first line here is what you get from this example. So in this specific case, what is doing, okay, what is doing is to fill. So we have the 1, 1, which is entering. The A is 1, 1, and the 1, 1 has an offset -1. So it finished here and here. So the main diagonal has offset equal to 0, which is K2. K2 goes with the B. So this is the main diagonal, and the B is just filled with 2, 2, 2, 2. And finally, the upper diagonal, which has an offset +1, is 3, 3. Okay, this is a way. I slightly modified this code with this 3-diag mod so that we can choose the size of our matrix, and after we fill, for instance, easily with numbers which are all equal. So for instance, so there are 3 numbers. The 3 numbers are similar to the A, B, and C as the example before. But you see here, in principle, one could put, I don't know, -2 and whatever. But what we are interested in is really a case in which we just have the main diagonal and the 2 diagonals just above and below different from 0. So I don't need to have arguments -1, 0, 1. And so what? To fill completely with, let's say, A, and after I can choose A equal to 1, as before, for instance, I can use that command. You recall that inside NumPy, there is a command called once. This once is a command that produces an array containing n-1, containing n-1, once n-1 contains n-1 objects. For instance, let's take this one, which is the main diagonal. Once n, if I take n equal to 5, contains 5 objects, and it is 1, 2, 3, 4, 5. Okay, so on the main diagonal, I have 5 objects that initially I put all equal to 1, and after I just multiply by a constant And these are the elements with which I fill the main diagonal. Does it make sense to you? Essentially, what he wrote here is okay, but it's not very handy if you have a big matrix, because you don't want to write 1, 1, 1, 1 300 times. So you can make this automatic, and you can just introduce first an array containing all ones, and after you multiply the ones by a number, all of them. You recall that this is a very handful command that you have in Python. Y m1, y minus 1, this was the offset, is an array having a range n minus 1, contains n minus 1 elements. And if I take an array and I multiply the array by a scalar, a is a scalar, is a number, I get an array with the same length, but where each of the elements is multiplied by a. Okay. And similarly I did for B and for C. I don't need to introduce a y plus 1, because since I am concentrating just on the specific case in which I have just the upper and the lower diagonal, they have the same length, which is n minus 1. Okay, so I fill ones with all ones, okay, and after I multiply by B or I multiply by C, and I am happy with that. Yeah, you see, I multiply by A, multiply by C, the same object that contained just this 1, 1, 1, 1. And if I put everything together, so after I add together these three arrays, and it produces a matrix, which is this matrix here. Do you have questions concerning this? Because this little basic technology we are going to use many times. Is it clear enough for everybody? Yeah, okay. So this is what I after I printed it, okay, 3 diagonal, 1, 2, 3, dimension 5 is this animal here. Final thing, even though for the moment we are not using, but I want to try to use in some of the next lessons. If I have to do, if I'm dealing with a 3 diagonal matrix, and I want to do something connected with linear algebra, there are specific routines for doing linear algebra with, for instance, 3 diagonal matrices. I mean, for instance, if you have this matrix K, which is 3 diagonal, you can solve a problem KU equal to F, not using a generic routine for linear algebra, but by using a specific routine in which you pass the information that K is 3 diagonal. Today we are not yet using that, but I want to try to implement that in some of his codes, okay, because I think it's quite interesting to see in concrete how it works. Here is just a trivial example that I got from internet. So there is another package, I think I mentioned it, which is called Scientific Python, SciPy. And inside this Scientific Python, there are a lot of very interesting programs, for instance, of linear algebra. Let me just show you something. Maybe I can even share with you this. Okay, to recall now how to share again. Just a second. To add is again, where is it add? Lo vedete voi dov'è? No. Sopra? Ah, eccolo, scusate, grazie. Ok, allora, let me share also a few other things that can be useful. Dunque, yeah, for instance, this couple of things here are probably useful. 1 and 2. Yeah, I hope. Open. Okay, so now I have to write something as linear, tridiagonal. Okay, post. Okay. So these are two little routines that are explicitly using the fact that we are not dealing with generic matrices. So for instance, let's open this high tridiagonal. Maybe it's even already open. No, okay, sorry. Let me open it somewhere. Banded. Sorry, I have to find it now. Documents, sezioni, metodi. Okay, let's start with this one, for instance. Okay, so this you can find in this scientific Python area. And this specific code here does something that can be useful. If one has a real symmetric diagonal matrix, which is exactly our case, this code computes eigenvalues and eigenfunctions in a very efficient way. I mean, it exploits explicitly the fact that it is not a generic symmetric matrix, but it is tridiagonal. Okay, you can have a look at it if you like. And I just checked how it works here. So essentially, the idea again is very simple. If it is tridiagonal, you don't need to pass too many informations. You can, for instance, just tell that on the diagonal, you have, for instance, 4 elements or equal to 3, which is this, 3, 3, 3, 3. And recall that this is specific for symmetric tridiagonal. So you only have a main diagonal and another piece of information. So the other piece of information is the other -1 3 times, both above and below. Okay, so these are the information that you are passing to this numerical code. And at that point, the numerical code, this high tridiagonal of D and E, computes your eigenfunctions and eigenvalues. And in principle, after you can even reconstruct, of course, your matrix to check that what you did was correct, etc. So, for instance, let's have a look here. Okay, so what? Yeah, what I did here was okay. So, okay, I defined the matrix. I called the program A tridiagonal, so I'm computing the omega, which are the eigenvalues, and the V, which are the eigenvectors. And this is the matrix that essentially is exactly the same way of writing as we have already seen using diag. And this is what we get. So the matrix That is what I print first here, is what we were thinking, 3, 3, 3, 3. These are the 4 eigenvalues, and these are the 4 eigenvectors. The point of this algorithm, as I said, is that it uses, I mean, we are not going now in the details of the algorithm, but it's important to keep in mind that this is an example of an algorithm which works only for symmetric diagonal matrices, but is, of course, much faster than a generic algorithm that exists, of course, for a generic symmetric matrix. Okay, I can of course invoke a generic algorithm computing eigenfunctions and eigenvectors and eigenvalues for whatever symmetric matrix, but it would be much lower. The number of operations that this program is performing is significantly lower than in the general case. Okay, so for the moment, we are not yet using this type of things, but we'll try to write some code making some usage of the fact that it is tridiagonal. Let's go to our example, which is here. So the example 518. So we have to slowly understand how to translate, so to say, into Python what we discussed before. So the first thing, let me run maybe the code so that we see what we get. Okay. So the first thing, so the equation you recall is the trivial equation minus second derivative equal to E of X. Okay. And and it is between, let's say, between 0 and 1. Okay, between 0 and 1. So the first thing is to build that basis of triangular functions. Okay. So this can be done using this piecewise command that is again inside numerical Python. So let's have a look in concrete how this works. So I am defining each of these functions, the elements of the base. So which are the ingredients? There is an index, of course, because you recall they are centered at a specific point, xi. They depend on x. And I also decided, this is just my arbitrary choice, to introduce the step h as one of the arguments of a function. You could do in different ways. I mean, it's not necessarily the way I'm doing is the best or the most elegant or whatever. At least it works. So how is defined this piecewise? It's very simple. Essentially, what you do is a list of conditions. 1, 2, 3, 4 conditions. And for each of these conditions, if one of these conditions is satisfied, let's say the first is satisfied, then you get a number. So first condition, you get 0. Second condition, you get this. Third condition, you get this. Fourth, you get 0. Okay, so there must be, of course, an exact matching between the number of conditions, which must be mutually exclusive, because we want to have a piecewise function. So, I mean, this is what happens for x smaller than, this is what happens when x is between this, and so on and so forth. So, again, let's have a look. If I am concentrating on the element phi I, you recall that the element phi I is centered at the point xi. The point xi is I times h. For instance, x1 is h, x2 is twice h, so on and so forth. And it is different from 0 only on the left and on the right of xi, and only for a length equal to h. Otherwise is 0. So it is 0 if x is smaller than I minus 1 times h. It is 0 if x is larger than this. Instead, if we are on the left, it is that expression that I wrote before. This is a little component of straight line that connects, let's say, 0 with 1, something like this. And the second, different from 0, is the other part from here to here, let's say. An important technical point that at first I wrote it wrong. There is this end. So this end is the logical end, telling that this is true only if both these conditions are satisfied. So if x is larger than this, smaller than this. There is this little technical point. You must put these two brackets. You must put the bracket here and the bracket here. At first I did not put, and Python was complaining. Why? Because AND works between two logical variables, logical quantities, something like true or false. And if I don't put the brackets, from what I understand, I am not forcing Python to really evaluate what is written inside. So when I put the brackets, I am telling Python, okay, evaluate all this quantity here. This quantity, notice, is a Boolean variable because it's a condition. So this is either true or false. But if I don't put the brackets, Python gets stuck, does not understand how to mix together some normal numbers, logical variables, whatever. So you must put these two brackets, this one and this other pair of brackets. Okay, so this is concerning how to write the piecewise, and this is, of course, a plot of a few of these piecewise. Let's just have a look. I used the usual trick. So this is the function, and I want to plot the function. One way for doing that is to introduce a grid, okay, and essentially, and after evaluate this function of all the elements of the grid. So first of all, I vectorize the function. I mean, these are little details, and I mean, of course, conceptually there is nothing, but if you don't know them, it doesn't work, simply. And unfortunately, all these details are different from Python to Mathematica to MATLAB to whatever. So one has to spend some time in learning the little details. That's it. And so, for instance, if you want to use this function, fun, with an argument that is not just a number, but is an array of numbers, you have to first vectorize it, what I've done here. So I have a vectorized version of fun. And, okay, forget about this. I just wanted to check. I mean, I need to check systematically if what I am doing is correct or not. So I printed something. Let's jump here. We don't really need this. We can even comment it. Where is the comment? Here. Okay. So what you want to do is to make a plot instead. It's much better than just evaluating a few numbers. Evaluate the function for a few numbers. So you start by building the values of the independent variable on which you want to evaluate your function. For instance, this lean space in 0 and 1, 101 points. And so now this T is an array containing 101 points from 0 to 1. And now I am evaluating the function vfun. Recall that fun has 3 arguments. The first argument, I, just tells which of the n-1 functions, the first or the second or the third or the ninth. Okay. And sorry, I'm lost now. And okay, so I have this, I evaluate on T, which is this space, and H is, as you recall, the step, the distance between two of those points. So I choose 0.1. Okay, 0.1 is the step between points on the grid. So I did this 1, 2, etc. So this works in the sense that if I have an interval 0, 1, if I have an interval 0, 1, and I want to divide in 10 subintervals, then the step is 0.1. Okay. And after I plot, so what I do, I have generated both the array of the independent variable and the 4 arrays of phi 1, phi 2, phi 3, phi 9. And here I am plotting. And these are the objects. Phi 1 is the blue, phi 2, phi 3, phi 9. So again, we notice that we don't need the phi 10 and we don't need phi 0, because an hypothetical phi 10 would be centered here, and phi 0 would be centered here. But since the function is vanishing here and here, we are happy this way. Okay, so this is the first point. Second point is the matrix. So we use what we have learned a moment ago. So what we learned a moment ago is how to write a three-diagonal matrix. This is a three-diagonal matrix, and so I just reintroduced the definition because this is not this three-diagonal modified. I mean, I wrote it, it's not inside Python, okay? This is a way of writing a three-diagonal matrix, okay? It's exactly the way this object here, okay? I'm just using now, okay? So this three-diagonal, it uses just the ones of numerical Python and the diag that builds diagonals with a certain offset. And after you put everything together, and you have your matrix. And in our specific case, we want to have n equal to 10, where n is the number of subintervals, and therefore h is 1 over n, and therefore our K matrix is this object here. Because you recall that is three-diagonal. On the diagonal, it was 2 over h. On the 2 diagonal with offset -1 or +1, it was -1 over h, -1 over h. And finally, a little point, we start with the element 0. So recall this, when we have an array, or when we have a matrix in Python, recall that they are labeled starting with 0. So this sometimes can be quite annoying. And I must admit that I have still to come to terms with it. But okay, that's it. I mean, we have to recall that the first element is called 0 and not called 1. And the other thing is how many of these functions we need. We need not 10 functions, but n-1, 9 functions. Okay. So this object here is our three-diagonal matrix that is appearing now here. In principle, we have to be slightly careful because I count 1, 2, 3, 4, 5, 6, 7, 8, 9, but Python counts 0, 1, 2, 3, 4, 5, 6, 7, 8. So when we it will happen that we need to use one of the elements of the matrix, of the array, or whatever, we have to keep in mind of that. Instead, just get it wrong. Okay, second point is we need to evaluate the matrix elements of the function f projected on the basis. So since the f was just an exponential, in principle one can do this analytically, but let's be more general. Let's try to compute this numerically. So how do you do? You can, from this scientific Python, for instance, use that little numerical code called quad that I already mentioned a few lessons ago. This quad is quadrature. So it's written here, is computing an integral of a function, which must be defined between a and b. And there are a lot of options which are good because sometimes you really want to use these options, but we will not for the moment at least. And instead, another important ingredient is this args. This args, that is written, you see here, correspond to the fact that you have your function, and our function is in principle a function of x and I, but we want to integrate on x, not on I. So we have to tell Python that there are a certain number of quantities which are parameters. And this is what we are doing by introducing these args. Args equal I tells that I is not a quantity on which to integrate. And finally, this bracket 0, as you recall, is because the result of quad is a number and an error. And the first, so is a sort of array containing two numbers, the first of which is the element 0, is the integral. The element 1 would contain an estimate of the error. And that's it. So at this point, we have to generate our column F, which is here. And again, what we can do is, I mean, there are plenty of ways. I'm sure that there are more elegant ways. But this morning I was at a certain moment quite tired and decided that this was good enough. So I generated an array, again, an array of length n-1, just fill it with ones, because after I'm just going to substitute. And after I take each of these elements, and instead of having ones, okay, so this index I is ranging again between, recall that when I write range, I actually go from 0 to n-2, okay? So it contains n-1 elements, but is 0 and -2. So this Fi is what? Is the integral of fun1, and fun1, oh sorry, this I've not commented. Fun1 is defined here. Fun1 is the product of each of the elements of the basis multiplied by exponential of x. And this is NP exponential of x is, okay, just exponential in NumPy. So this is the function that I want to integrate between 0 and 1. That is written here. I want to integrate this function that contains, okay, notice here that fun1, I already eliminated h. H is a parameter, so to say, that I have chosen, but after I have this, it's probably not the best way. This need to be written better, because I think it would be much better to keep h inside here, so that after we can change, for instance, we can change h, for instance. It's not written in the best way, this program. Sorry, I rushed to write it down this morning. It works, but it's not written in the most precise, elegant way. you can maybe improve on it. Anyway, h is given here is 1 over n. Okay, so h is known. Okay, from here. So at this point, I don't need to keep writing h, but it's not really elegantly written, I must say. So we integrate fun1, where the argument, oops, sorry, this is not really correct. This is, the argument is I, not I plus 1. I don't know why I wrote, sorry. The argument is I. Okay, I don't know why I wrote, no, it probably is even correct because I want to evaluate fi substituting instead of I plus 1. Okay, maybe it's correct. I have to think a moment. You can maybe also think about that because I think that the result is correct. I'm not so sure how I wrote it, but okay. And finally, so this point we have defined F. So this is the matrix. This is this object here is the array containing the elements F 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the matrix is 9 by 9. This is 9. And finally, I just call a generic algorithm linalg that is essentially computing the solution of the equation Ku equal to F. And I give just K, that I call the K matrix here, and F, which is this array here, and this little code computes the coefficients. And I printed the coefficients here. These are the 1, 2, 3, 4, 5, 6, 9 coefficients. What do I do with the coefficients? I build the solution. So the solution is a sum ranging from 1 up to n minus 1. So what is written here? Recall that there is this offset, but the offset should be fine because each of these objects is shifted, so to say, to the left by 1 unit. It's not 1 to 9, but 0 to 8. So if I do for each of these objects, I should be okay. I really don't like it, but that's it. And so I have to write a sum, and so a sum I can write by initializing to 0, and after telling that I systematically add a new of these objects. The objects are each of the coefficients that I just computed here, multiplied by the function, and that's it. At this point, I can check, and this sol 0.3 is the value of the solution, evaluate 0.3. So one thing that you can do is to try to improve. It's not really written very elegantly. And also, I really ran out of time this morning. Instead of printing just the solution, you can plot the solution. So what you can do is, as before, you can vectorize the solution, and after you compute the vectorized solution on each of the elements of the grid, the T, and after you can plot the two objects one with the other. Sorry, this morning it was really late, I could not make a plot. So what I suggest, I'm pretty sure that this program that I wrote, okay, seems to work. I checked the result with the one that I wrote with Mathematica, and they're exactly the same. So it's not completely wrong, which is already something. But I'm pretty sure that can be written in a more precise way, etc. And you can make a plot. And you can compare, for instance, the exact solution that was exponent, that we wrote before, the analytic solution, with this approximate solution. So I suggest try to play with it, try to improve it a little, because it's certainly not the optimal writing, okay? So we still have some time, and let me discuss with you a little numerical problem that can be useful now in the future or whatever. The little numerical problem is how to compute derivatives. I mean, in this case, you recall we had to compute some derivatives of the elements of the base, but that was extremely trivial because the elements of the base are linear functions, the derivatives are just constant, okay? But of course, there are situations in which it is very heavy to compute the derivatives, and Python can compute the derivatives. There is the symbolic Python, but after it can become a little bit messy because you have to invoke symbolic Python, you have to transform that into a function that you can use, and so on and so forth. So let me discuss with you this problem of how you compute derivatives using not just Python, but in general numerically. I got this little program. It's nothing special, but it was already done by a book. I think is I share with you, isn't it? I share with you with codes. I sent you. Is it true?
Yes. Yes.
Okay. Okay. So this is one of the codes inside that package. That is this Getzerlis book. Okay. It's nothing special, but is interesting to understand the problem. So let me first state which is the problem. So the problem is how you evaluate numerically the derivative of a function. Of course, what you can do is to try to use the definition of derivative. And as you recall, when you learn this at the first year math, is the limit for h going to 0 of this incremental ratio, no? And of course, we can try to use it, but there are a lot of caveats. So, okay, whatever is the function, this function here, f, okay, and this is the derivative, okay, this is the exact function, of course, and this is the exact derivative. Okay. And now let's introduce an approximation, which is I try to evaluate the derivative by incrementing by a quantity h minus f of x divided by h. This can be done, but it's not the best way of computing the derivative. Because as you probably already mentioned it, now I don't recall, imagine that you are making a series expansion of f of x around x. So if you make a series expansion, what happens? That f of x plus h is f of x plus h f prime of x plus 1/2 h square f second, etc. So if you compute something like this, okay, the first term f of x just cancel. So after you get, of course, f prime of x minus f of x times h divided by h. But of course, there are the other terms in the expansion. The next term is the terms containing h square. So, and you are essentially neglecting in the sense that if I expanded f of x plus h in a series, I cannot arbitrarily truncate the series. I mean, I can, but of course I'm making an error. The error that I make truncating the series contains an h squared. Is divided by h, okay. So it means that the error that I am making using this expression to evaluate f prime is of the order of h. maybe I write it, I don't know if it is completely clear. Let me just write it here, just it's crying automatically. Okay, the page, derivative. Oh, let me write this. Oh, now it's enormous. You see, this is very strange. I don't understand how is working. Try this. Okay. F of x plus h. Okay. I know that if f is regular, I can write of f of x plus h f prime plus 1/2 h square f second plus. So what happens if I take f of x plus h minus f of x divided by h? Well, of course, the first term cancel. The next term is f prime, and I am very happy. But after, there is another term, which is h half f second. So what does this mean? It means that if I define, so to say, let's call it, I don't know, right derivative of f is defined in this way, okay, then I am computing f prime, but I know that I am introducing an error which is linear with h. And as you can imagine, exactly the same works if I compute the derivative, let's call this left derivative of f as f of x minus f of x minus h divided by h. Also, this one is essentially exactly the same, will contain an f prime, and probably here I get minus, I think, h half f second, meaning that again I have an error of order h. Funny enough, I can do better. This is really too large. Let me restrict slightly this. I can do better. I can define a central derivative of f, which is f evaluated at, let's say, x plus h minus f at x minus h divided by 2h. And the reason is that if you expand again everything, you are this time cancelling the terms in h squared. Let me see if it is true. Let me see if it is true. So if I write 1 over 2h, so I expand the first and I get f plus h f prime plus 1/2 h square f second plus, okay, now, okay, it would be 1 over 3 h cube f 1 to 3 minus, this is f minus h f prime plus 1/2 h square f second minus 1 over 3 h cube f 1 to 3 closed. Okay, and therefore this cancel, and therefore the net result is that this is equal to f prime, because I have h plus h, 2h, with an error which is of order, this time is h cube divided by h, so is of order h squared, while here the error was of order h. Okay, this is quite important because it means essentially that if h is a small number, I can get a smaller error using the second technique, the central derivative, than using the right and the left derivatives. One could imagine that all this is nonsense, because after all, I can take h as small as I like, and who cares if it is order h or h squared. Unfortunately, it's not like that, because if you are working with a computer, you have your numbers which are defined with a certain number of digits. So what typically happens that if you take h, which is so small that the value of the function evaluated at x plus h and at x becomes comparable, because as I said, there is a finite precision in the way you are writing everything using a numerical code. I mean, if you take h too small, f of x plus h and f of x becomes comparable. And when you make the subtraction, only just a few digits survive. And that means that the smaller you take h behind a certain point, and after you start increasing the error. Okay. So let's go back a moment to that little numerical code. So that's why we prefer to use this symmetrized version, the central derivative. And here there is a little example. Oh, sorry, let's run the code. Okay, so in this code, what it's doing is to try to compute the derivative of the function, the derivative of this function here. This is the exact value at a specific point, 0.5. Okay, and comparing with the exact result, which was this f prime. Okay, and what you can do is to check what happens if you are reducing the value of h. So you start from 10 to minus 1 down to 10 to minus 12. And what you are doing, you are systematically comparing. You take the absolute value of the difference, between this approximation to the derivative and the exact value, or this approximation and the exact value. This approximation, exact value, with exact value. And h is a quantity which is running. This is another way of introducing a loop. Okay, so this hs is an array. Is an array containing 12 elements. Okay, and now I tell that h is each of the elements of this array. Okay. And these are the results. This is just a way of printing the results. So he wants to print the results. He wants to print a first line containing this information, which is just this, print in this quotation marks. And this is just this. And after he wants to print h, these two errors. Okay. And essentially, he wants to use a format. Oops. The format, just a second, sorry. The format is this format here, ROV. Okay. So this format tells essentially what? That you have three numbers, 1, 2, 3. The first number, you recall that they are counted from 0, 1, and 2, the three numbers. The first number is a number written in the, how is called, scientific notation with exponential, but this number has 0 digits after the dot. while the other two numbers contain 16 digits after the dot. So this is a number written in the exponential notation, no digits after the dot, and this contains 16 digits after the dot. So he wants to print this, this, and this, and that's it. Okay. So let's have a look at the results. So the results are, this is what you get if you take the, I think that F is for forward derivative, central derivative. So of course the error initially goes down, but notice that the error starts increasing. Because at a certain moment, when you arrive for values of h smaller than 10 to minus 8, you run into the problem that I was mentioning. And if you compare with this other object, you can see that the errors are significantly smaller. These are essentially linear in h. For instance, take this, h is 10 to minus 4. This number is of the order of 10 to minus 1, 2, 3, 4. While here we have 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this scales like h, and this case like h squared. So in general, we will try to use, whenever possible, these central derivatives for computing the first order derivatives. There are similar formula for other order derivatives and so on and so forth. Okay, I think that for today we are set. What sorry, I wanted to show you another thing. I forgot now. It was the other file. I'm lost now. Where I put it? Yeah, here. So I just wanted to tell you that, for instance, this is an example of a code which is solving the linear equation, again, ax equal to b, but A is a bounded matrix. So bounded matrix means essentially that you have a finite number of diagonals above the main diagonal different from 0, and a finite number of diagonals below the main one different from 0, and all the other rest of the matrix is 0. In our case, it would be 1 and 1. So this this code uses an algorithm which is optimized for this type of matrices to solve. So we can use this scientific Python. This linalg is a subdirectory of scientific Python containing linear algebra, and specifically this program called solve bounded. Okay, how does it work? Okay, there is a first step that one has to rewrite the matrix in a specific way. Okay, this is just to do, I mean, one is just to rewrite the matrix so that, notice that instead of having the diagonals different from 0 going from up, left, down, right, is written in this way. Okay, one has to do that. Let's see. Okay, so after you have rewritten your matrix in this way, so you start from your matrix A, you rewrite it as AB in this way. At that point, the program is easy because what you pass is L and U, meaning that is the number of not vanishing diagonals in the lower and in the upper part, below and above the main diagonal, AB in this object. And of course, B is what in our case was F. And what it gives you back is the solution. So it's rather easy. It's here. So you just, it's very similar to what we did. I mean, the only difference is that first you have to rearrange your matrix in this way. So you go from initial matrix, let's say K, you rearrange in this way, and after you call this program and okay, and what you get is the solution containing the various elements. So this, I think, is worth considering, and I will try to use anytime that is possible this specific version respect to the generic one, because at least conceptually, this is the one which is making real use of the finite elements technique, while the other one is rather generic. Okay, if you don't have questions, comments, or whatever, we stop here and try to play a moment with this. So try to improve what I did. I had all this done nicely with Mathematica, and but unfortunately, this was a nice example here. But unfortunately, I had to rewrite now everything with Python. So this was so this is what you should get. Okay, this is the solution that you have defined, and here, for instance, I was plotting the exact solution and the approximate solution, and you should get something similar to this. The number that I just plotted the solution as 0.5 that is sitting here and is very close to 0.2, 0.195, etc. So it should be correct, but you better check. Okay. Okay, that's it. And if you don't have questions, see you next week. Have a nice weekend. And bye.
Thank you. Bye bye.
Thank you, bye.
Arrivederci. Ciao, ciao. Ok, dunque devo disconnettermi. E devo chiudere, credo, questo. Devo anche chiudere la registrazione o secondo voi viene in automatico? Forse se lo chiudo, stop recording. Anyway. Stop recording.